Welcome once again to quantum field theory. We're finally getting somewhere in this course. We're finally learning how to do an actual quantum field theory calculation. Last lecture I introduced things called the Feynman rules. So if you remember, what are they for? Well, the Feynman rules are a way to compute this particular quantity, which, while by itself is not directly observable, is directly related to things that are, namely scattering amplitudes. So the Feynman rules tell us how to compute this thing in the case where our Hamiltonian is the sum of the Klein-Gordon equation term and a quartic interaction. So if you recall, this object is defined with a time ordering S operator is defined thus. And we work in the interaction picture, and our Hamiltonian throughout is a sum of the Klein-Gordon equation Hamiltonian, Klein-Gordon field Hamiltonian, and this quartic interaction term here. Quartic. So, and we commenced in the past lectures the study of this observable quantity via a perturbation expansion in the smallness of lambda, where I've always been stressing and will continue to stress that even though lambda may be small, like 10 to the minus 3 or something, this doesn't mean that this operator here is small. Nonetheless, we will pretend that it is small and see what kind of results that we get, and then match them against experiments, and if they match, then we're happy. That's the metric for success in this course. And what we showed in the previous lecture is that this is a sum of all diagrams, of all possible diagrams with n external points, subject to some rules. Which I'll write out here. Feynman rules in position space is what we covered in last lecture. Now, to be clear, I did not prove this statement here in the previous lecture. What we did is we did a perturbation expansion to order lambda for a 2-point Green's function, and did not consider the case of n external legs at all, and did not consider the case of lambda higher than 1, the power of lambda being higher than 1. So to the extent that this is true, all we can say is that we know that this is true in the very special case where n is 2, and we sum all diagrams with 2 external points and 1 vertex. We've checked that. That worked out. But beyond that, we haven't checked anything. So I'm going to put an exclamation mark there. It's not that difficult to convince yourself that this result is true. I'm not going to prove it in this course. There's a bit of combinatorics you have to set up to make it work. But I want you to just try it one time. First convince yourself that when n is odd, that there's no diagrams with n external legs. And then start doing some Taylor series of this exponent here, looking what kind of fully contracted terms appear, convince yourself that these can be bijectively mapped with diagrams, and then you are more or less complete. So in this course, I'm not going to prove this statement here in generality. I just argue that it's plausible, and then we'll work with that as essentially as a definition. So what are the rules? Assuming that this is a true statement. What are the rules? Well, we wrote them down in the last lecture. For each propagator, which is a line with two vertices at its ends labeled by position x and y, we associate the value Feynman propagator of x minus y. So that's rule number 1. For each vertex, we associate an integral minus I lambda d4 z. This is the formulation we ended up with in the end because it matches the combinatorics slightly better to do things this way. For each external point, remember we had this notion of external and internal. Yeah, a question?
In the previous lecture you didn't make the minus sign, but I think here it's correct.
In the previous lecture I didn't make a minus sign. In the last, when I wrote out the Feynman rules, is that correct? There was no minus sign here. Okay, that was a mistake then in the previous lecture. I mean, you don't have to put the minus sign in here, but you'll have to keep track of it somehow. So yeah, there should be a minus sign in that rule here. So this is the canonical rules. These are the fully general rules, right, that we're going to use for this course. And you can regard the discussion of the previous lecture as a motivation for these final set of rules. So for each external point x, we associate the value 1, which seems very boring, and why would we bother? But we're going to see that later on in other theories that this external value here is very convenient to let that change. And finally, we've got to divide by the symmetry factor, which is this somewhat difficult to calculate quantity, which measures how many times a given diagram appears in this Taylor expansion. That's it. That's how you do a full calculation in quantum field theory. Now, it may not have escaped your attention, I hope it didn't escape your attention, that the answer you get applying these rules very quickly becomes infinity. Like within an order or two of this Taylor series, you're going to get the number infinity. Now, there's various reasons for these infinities, and we're going to cover some of the reasons in this course, and only properly the other reasons in the next course. So first of all, there are no infinities in quantum field theory. Let's get this clear. You only get infinities when you ask the wrong question. Now, the difficulty is in finding out what is the correct question to ask so that when you apply these rules or some modification thereof, you don't get infinity because you don't observe infinity in nature. It's kind of a cool question, actually. I've been asking this for years. Can you think of a single experiment or even set of experiments that would prove that some quantity in the universe is actually infinite? I want you to think about that. Like one example, an example answer to this question, which isn't quite an answer, is like the hydrogen atom. Well, you know the spectrum of the hydrogen atom is essentially infinite up to the Rydberg energy. There's a sort of countably infinite number of eigenvalues up to minus 13.6 eV. But have we done an experiment that actually probes all of those infinite levels? We're pretty sure it's infinite, but maybe it's not. Is there any quantity in the universe that we know is infinity on the basis of some statistical experiments that we've done? So that's my question for you. I've been asking it for years. I don't think anyone's given me a satisfactory answer yet. Another near miss is scattering theory. The fact that we have continuous scattering theory work as a model for experiments is a pretty good hint that something's kind of infinite there. It's not good enough though. It needs to be actual proof. Right, well, infinities aside, whether they exist or not, the reason you get infinities in quantum field theory is simply because you asked the wrong question. Now, finding the right question is a bit more subtle in quantum field theory than it is in other parts of quantum mechanics. An example of an infinity that you tend to get very often in quantum mechanics is infinite ground state energy. That's something that you've probably encountered in various cases before, even before quantum field theory. And the standard argument there is, well, we cannot measure the ground state energy. That's not an observable quantity by itself. Only energy differences are. And so an infinite shift is clearly not a problem. Now, it turns out a lot of infinities that we encounter when applying these rules are of that nature. They're just infinite because you can shift them away and you don't get an infinity afterwards. Those are tame, not controversial infinities. And today we're going to dispel many of those. We're going to get rid of a majority of the infinities that come from just redefining things like changing the zero of energy. And that will come under the title of vacuum bubbles. We'll deal with those infinities. There are more troublesome infinities where you actually are left over with amplitudes that really do appear to be infinite. And for that you need to do a bit deeper physics. And that's what we have this body of work called renormalization theory to deal with. That's another way of saying ask a different question. Good. So that's Feynman rules in position space for phi-4 theory. Oh, I didn't say phi-4 theory. You will get different rules if you put in phi-3 theory or phi-7 theory. In fact, in the exercise class, I think you will have to do phi-3 theory. You'll have to work out some processes in phi-3 theory. It's a very good example. And you'll have to adapt these rules accordingly. You have to work out what the rules are. Now, I've done the Feynman rules in position space, but it turns out you can do everything in momentum space if you want, right? There's nothing that stops you from expressing things in terms of momentum space. So this Feynman propagator thing, it has an expression. You know, we could express it in terms of Bessel functions or whatever. But you can also express it as a momentum in an integral in momentum space. And when we do that, we see that we could as well have done all of our computations in momentum space. So curious. Somehow lost my notes for the momentum space. Well. Okay, I'm not going to do that then for the moment until I relocate my notes on momentum space because I don't want to make a mistake there. Instead, we'll talk about vacuum bubbles. Oh no, here we go. No, that was right in front of me the whole time. We have this expression for the Feynman propagator in terms of a momentum an integral in momentum space. Here it is, right? It's just this Fourier transform. So everywhere you saw a delta f x minus y in the perturbation expansion for the Green's function, we could stick in this integral, do the integrals with respect to the position space variable z, and then we'd just be left with integrals over momentum variables. And then, if you did it that way, you don't really win very much. You just have a different way of writing out exactly the same terms. But this other way of writing out exactly the same terms might occasionally be more helpful. It might help you see cancellations that you wouldn't be able to see before. So the answer we get then for this Green's function in momentum, if we did everything in momentum space, is sum of all diagrams subject to the Feynman rules in momentum space. It's sometimes convenient, especially in scattering theory, when you have states with a definite momentum coming in or a near definite momentum, to work in momentum space. There is some advantage to this. And also, it's probably the nicer way to see certain cancellations and symmetries in these diagrams. So what do? Well, for every propagator, the rules are almost the same. In fact, I'm going to leave them sort of on the same two boards here. We're going to have different diagrams. We're going to have diagrams with arrows on them. We're going to have oriented diagrams. So for every propagator, we now have an oriented line, and that's equal, and we put the value p on this line to indicate that momentum p is associated with this line. And we associate this rational function here to such a directed line. So, yeah. Rule 2 for each vertex. With all the arrows pointing in, we associate just the number minus I lambda. For each external point, we associate no longer the number 1, but in fact e to the minus ipx. There's an additional rule from what before. We impose momentum conservation at each vertex. We then integrate over undetermined momenta. So if you impose momentum conservation, you may not in fact determine all the momentum variables. And then you divide by symmetry factor, this last bit. then you just have to, okay, so the question is what happens if you have a vertex where one of the arrows points the other way? And you just have to associate them to each line, you associate a p, and you're just going to have negative p on that associated with that line. Good. We will not do so many calculations in momentum space, I think, or only maybe later. I'll come back to these rules later. So for the moment, I just mentioned them here for completeness sake. Now we've got, this is the basis for all calculations now in perturbative quantum field theory. You express all the quantities you want to calculate in terms of Green's functions, and then you deploy these set of rules to calculate these Green's functions. Now this is, it's worth stressing how amazing this is as a representation. It simplifies incredibly the combinatorics that we have to do, at least at low orders. It gives us a nice, convenient representation for all those terms in these Taylor series that we derive. So remember how tediously in the previous lecture I wrote out the series for the numerator, the series for the denominator. I did the division of the two series, very tedious, very boring, not much structure that you could see. With these diagrams, you have this pictorial representation for all the terms in the series, and that allows you to enumerate them in a very efficient way. And so, especially at low orders, this is a far superior way to represent the calculations. You don't have to use the diagrams, but I recommend that you do. Now, there is one thing that we noticed. If you remember, we had this series A0 plus lambda A1 plus dot 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 dot. In the previous lecture, that we did this calculation all to order lambda, and we observed a somewhat mysterious cancellation, right? So we had this guy plus this guy plus that guy. And we observed that after we expanded these terms out, then this term here vanished. It cancelled out. And that's really good, right? Because this thing here, if you evaluated this diagram, you definitely get infinity. It's definitely an infinite quantity, this thing here. And there's also an infinite quantity up there. So you've got to wonder, is this cancellation we observed in the last lecture, a miracle? Or is it a more general result? And the great thing is that it's actually a more general result, and it allows us to cancel off a lot of very unpleasant infinities that have no operational meaning anyway. So these, the fact that that infinity there cancels exactly with that infinity there tells us something about the nature of those infinities. So we'll see that it's the form of a redefinition kind, like when you change the zero of energy. So that's the objective today, is to actually prove, we're going to be able to prove this, that all the diagrams of this kind that cause infinities like that up here will in fact exactly cancel with their counterparts here in the denominator. It's pretty amazing. I'll write out that cancellation from the last lecture. That's it there. And now we'll actually go ahead and prove that this is a general, is a clue for a more general result. So a typical diagram has a pretty standard structure. You've got some part that's connected to the external vertices, x and y, for example. Multiplied by some parts that aren't connected to the external vertices. So a typical diagram looks like this. It's a connected part, the diagram that's connected to the external vertices, and there's some other parts of the diagram which are not connected to the external vertices. They're called the disconnected pieces. So far so simple, right? Now the external vertices you might wonder, could it be that there's a diagram that we can write down where one diagram is connected to x and another one part of the diagram is connected to the y, but that the x and y aren't connected? You might wonder, is that possible? Well, the two external, at least in the NS2 case, that's impossible, right? The two external vertices x and y are always connected. And the reason they're connected is because their degree is odd. They're connected to an odd number of legs. But every vertex has degree even in the bulk. So if you did a walk on the graph and you did not visit the same edge twice, you would have to have another vertex with degree odd. So there cannot exist a diagram with a single odd degree vertex. So they must be connected. What we're going to do is list, it's these disconnected pieces that are the troublesome ones. And what we're going to do is make a list of all possible disconnected pieces up to planar isotopy. In fact, just up to combinatorial equivalence. Good. Now, the set of all possible disconnected Feynman diagrams is countable. So you can count, you can label them by the number of edges and vertices, if you like. That's a good way to count the possible disconnected Feynman diagrams. So we can at least write a countable list. It's an infinite list, but it's countable. And we'll start writing out this list now. So disk, as in disconnected, is a set, and the first element of this set is this diagram. This is the first disconnected Feynman diagram. In fact, there are no more with one vertex. So here's the next one. Here's the next one, it's melon graph, and so on. We could go on all day, but let's stop there. I'm going to call this D1. This is D2. This is D3. This is D4. And as I said, it's a countable set, so we can assign a unique D sub n to every diagram in that list. Now, according to the Feynman rules, we could evaluate the value of these diagrams, assuming that it was finite. So the value of diagram dj is called vj. Simple. Now, all of these values are infinity. They are all infinity. And this is a serious point. The way we have to interpret these numbers is we have to put a cutoff into our theory. Okay, this is the correct order of limits. I'm not going to say much about it now. For the moment, we're just going to assume that each of these vj's is a number and not infinity. But this is the first sort of hint at the way we're going to have to interpret quantum field theory. And that is, in any of the infinities in quantum field theory, you cannot, in general, put in the value infinity and then hope everything works out. The only way you can interpret the equations that we're going to come up with is that they are a recipe for many equations. They're a recipe for a quantity that depends on a thing called a cutoff that makes everything finite. You do all your manipulations in the presence of this thing called the cutoff, And only at the end do you insist that the answers for operationally defined quantities don't depend on that cutoff. I'm going to say a bit more about that later when we talk about the remaining infinities. But for the moment, it's sufficient to think that the values associated with each of these diagrams is a number, and it's a different number for each diagram, and that these numbers will obey the usual rules of arithmetic. That's all we need for this argument. All right, let's now start this argument. Suppose your diagram that you're interested in has nj pieces of type dj. Well, we'll be able to work out the value of this diagram using those Vj numbers that we've written up there. So let's evaluate the value of diagram D. The value of diagram D is the product, right, according to the Feynman rules, it's the product over all the propagators and integrals over the vertices, but in particular it's the product over the values of the disconnected pieces and the connected piece. So we can work out that the value of this diagram, of this single diagram, is given by this rather intriguing formula here. Very intriguing formula. We're going to do it for this diagram up here, just to double check that this formula makes sense. I'll move the board in a second. This is diagram D, an example diagram D. Let's work out its value according to what we think it should be and according to this formula here. So the value of that diagram D is the value of the connected part, right, according to the Feynman rules. It's definitely the value of the connected part multiplied by the value of the first part, first disconnected part, but that's a diagram of type 1 or D1, so that's just V1. Then it's multiplied by the value of the second disconnected piece, but that's D3, so this is V3 here. And then the third diagram there is a bit hard to see, but it's actually a diagram of the second type, V2. Now, is that equal to this apparently infinite-looking expression here? Let's check. Well, the number of diagrams of types 1, 2, and 3 is 1 each. So that certainly matches up these three numbers here. 1 factorial is 1, v to the power of 1 is 1, so that looks all good. And then how many diagrams are there of type d4, or 5, 6, and 7, and so on? Well, 0, right? So if you substitute 0 into this expression, that's 1 and that's 1. So indeed, that works out for this diagram. And it's pretty easy to see that the symmetry factor for a diagram is the disconnected pieces. The symmetry factor is indeed this. If you wrote down the same disconnected piece twice, then there's n factorial ways you could have written that down. So that's the reason for that particular symmetry factor. So that's intriguing. But let's see where it actually goes. I mean, this 1 on n factorial should start to make you think of certain things. So remember the rule? The Feynman rules tell us that G2 of xy is equal to the sum of all connected diagrams. No, not the sum of all diagrams but another way of saying that is it's the sum of all connected pieces. This is meant to say connected, and multiplied by the sum of all disconnected pieces times by the value. And the value we've agreed for a given diagram is this thing up there. Let's see where this goes. We've got sums, we've got factorials. It's looking promising. All we're going to do is commute sums around. Okay, not much happened here. I just pushed one sum past the connected bit. But what's going to happen next? This is where it gets really interesting. Very interesting, right? So, of course, summing over all assignments to these nj's and then taking the product is really the same as the product over sums of all the nj's. Think that one through for a moment. But now, wow, I mean, you know, that is highly suggestive, this expression here. That's just the Taylor series, of course, for the exponential. And not just any exponential, it's exactly the Taylor series for the sum of the values of all the disconnected pieces, one after the other. Ah. This is the numerator of G2. So just to be clear.
Question.
Yep.
The values of the disconnected pieces are infinity, aren't they?
The values of the disconnected pieces are infinity, yes.
So the sum doesn't converge.
So the sum doesn't converge in the worst possible way.
Why can we?
Why do any of these manipulations make sense?
Yeah.
Is that your question? Okay, I refer you to this text in this bracket here. So the way to interpret any of these calculations is you first put a cutoff on your theory which renders all of these values finite. I'll say more about cutoffs later. Then you do all your manipulations with these finite quantities, and then all these sums will converge in exactly the way a sum should converge. And then at the end, you look at you take the cutoff back to infinity. So it's this order of limits that makes sense. If you do the order of limits differently, nothing makes sense. Later on in this course, I'm going to argue that this order of limits is the correct operational way of doing things as well. In fact, we are always in the presence of a cutoff. So the cutoff is never infinity in any of these theories. So what I've written down in adding this 5-4 perturbation theory term is not a theory yet, because none of the quantities are finite. It's only a theory when it leads to finite numbers at the end. So I'll have more to say about that later, but at the moment you regard these manipulations, there's two ways to regard these manipulations. One, which I prefer, is this way. This is actually statements about a thing called a cutoff theory. Or the second way is that these are formal manipulations in some extended field that includes the symbol infinity. Whichever way makes you happy at this point, feel free to use it. You're right to be skeptical, but I promise that everything will be fine in the end. Yeah?
It may help if you explain what these cutoffs are.
Ah, okay. It might help if I explain what the cutoffs are. How about I do that in just a moment? I'll finish this derivation, and then we'll spend more time on what is this cutoff. And then, yeah, I guess we got time to have that discussion today. Okay, but assuming these quantities here are finite, then this is these manipulations presumably made sense. Okay, that's for the numerator, right? Similarly, for the denominator. If you do exactly the same argument, you'll see that in the denominator there are only disconnected pieces. And you will find precisely that answer, assuming that they're finite. Hence, we have this magical cancellation. This makes our life so much better. This exponential factor here cancels exactly against this exponential factor here. So the final result, modulo your concern about the values of these diagrams being infinity, is that we see that we can get this perturbative expansion for G2 x of y as a sum of all connected diagrams subject to the Feynman rules. And that's a much easier task. We don't have to worry about these vacuum bubbles anymore. And I can just write out the first couple of diagrams of this kind. But I see I've reached your tolerance for the presence of infinities in this course. So we're going to have that talk, the talk about cutoffs. So why not have it now? Let me just check that I've covered everything I want to cover. Yeah, pretty much. The same result holds for n is greater than 2. So there's an analogous statement for n is greater than 2. Now I did something in writing down these Hamiltonians which is operationally extraordinarily tendentious. So let's think back to the Hamiltonian for the Klein-Gordon equation. Forget the phi-4 theory, just Hamiltonian for the Klein-Gordon equation. So that's a quantity that has this kind of structure here, right? Oops, no half. Now we should pause and think very hard about what we've done in writing down this Hamiltonian. We've not only written down an operator, we've also, to have written down this operator on a physical level, what we've done is assumed the existence of infinitely many degrees of freedom. Right? That was before we even wrote down the Hamiltonian. Roughly speaking, we have a quantum degree of freedom per location in space-time. So the value of the quantum field is describing a quantum degree of freedom per every point in space-time. So M4 is just space-time. Now what evidence, I remember how I asked you this question earlier in the lecture, what evidence do we have that there really is a quantum degree of freedom at every point in space-time? Not a lot. So our best measurements to date can resolve distances, actually I don't know, but the picometers we can definitely do. I actually don't know what's the smallest distance that we can resolve at the moment with an experiment. I mean, it's pretty small, but it's not that small, right? In comparison to 0, everything's pretty large. So the best that we can say is that we can put bounds on this, the number of degrees of freedom that we can resolve. The distance between the degrees of freedom and how we can put bounds on it, but it's going to be a number at the end. It's not going to be infinity. So in writing down this quantity here, this Hamiltonian here, we not only gave dynamics to a bunch of degrees of freedom, we gave dynamics to an infinite number of degrees of freedom. What right did we have to do that? Well, we had the right based on extrapolation. It's a method that works extremely well in physics. You observe phenomena A occurring in one experiment, then you observe it in a second experiment which probes more degrees of freedom. Then you observe that same thing happening when the experiment probes even more degrees of freedom. You do it 100 times, 1,000 times, and at some point you become convinced that we're not just seeing an accident, but that in fact every degree of freedom that we've probed so far is modeled by, say, this Hamiltonian, and therefore why not every other degree of freedom, whether we see it or not? Why not just postulate that it obeys this Hamiltonian here? Because, we extrapolate from what we've seen to apply to things that we have not yet seen. Well, it turns out it's just wrong, right? We know on really very reasonable and solid physical principles that something's going to go wrong when we get to distance scales of the order of 10 to the minus 34. There are some fairly natural thought experiments you can do that should convince you pretty quickly that when you start to probe things at the Planck scale, everything should break down, and that it would be difficult to imagine being able to talk about space-time at length scales smaller than the Planck scale. I say difficult, I don't say impossible. So just the Planck scale alone should convince you that there's something operationally wrong and sick with writing down a Hamiltonian like this. Now it's okay in sort of vacuo of gravity. If gravity did not exist, then maybe you could make sense of operators like this in an operational way. But the fact is gravity does exist, so it's counterfactual. We have to accept that there is at least one scale in our physical that's forced on us by the physical theories that model the universe we live in. There's one scale beyond which we probably can't go without some serious modification of the theories that we're working with. Now, what do we do when faced with an observation like this? You have to do one of two things. One is you can just deny this observation, work in denial. That works rather well. And just pretend that gravity is not there, and then pretend that these theories make sense operationally. And that gets you a certain length, into a quantum field theory course until someone says, but there's that quantity there and it's infinity. And so we've reached that point. The other thing is you have to regard these objects as being effective theories. It's the only other option left open to you. This is the one naturally I prefer as an operationalist. This is the option that I feel that we're driven into by the observation that there's this thing called the Planck scale. I feel that the only way we can interpret a Hamiltonian like this is as an effective theory. So I've got to say what an effective theory is. I'll do that in a second. There's multiple ways we could define effective theory at this moment. I'll give you an example first of an effective theory so you can get a feel for why Here's an example. Navier-Stokes equation is a great effective theory for quantum chromodynamics. So we know that when we have a liquid and we do experiments on this liquid, it's very convenient to imagine that this liquid is a continuous media. But of course, none of us here would ever think that the liquid is as this continuous media. You know that if you get your electron microscope out, you'll perceive that there are molecules making up the water. So this is an effective description for the degrees of freedom you can measure at a certain scale. So let's write this down as a definition. An effective theory is something that is a good description of a system which explains all the observations you can make up to a given scale. So Navier-Stokes works down more, well, you could hope to the Compton wavelength of water. So as long as your experiment is on, say, the micron scale, then the Navier-Stokes equation is a good description for every observation that you can make of your system. But what happens if we extrapolate Navier-Stokes all the way to apply to these fictitious continuous media all the way to the Planck scale and beyond? Well, then you get a theory that's sick. Well, we think that it might be sick, to be completely clear, right? Navier-Stokes equation may or may not have finite blow-up singularities in finite time. I guess it's sort of unclear. So there's something wrong with the Navier-Stokes equation, right? What do we do when we're faced with this observation? Do we say that fluid mechanics is sick and that it's the end of science? We don't, right? We say, we admit that there's a scale beyond which this effective description no longer applies. A given theory might break down, and I'm not going to specify what breakdown means. You'll know it when you see it, right? You get an effective theory, you do a calculation, you get infinity, and then you're like, well, that's bad, right? But it might be that this infinity only appears above a certain scale, lambda, in which case you conclude that this theory only really applies to scales below lambda as an effective theory. And that above some scale, you have to correct this theory. You could imagine an alternate reality where we thought everything was fluids, and that as our experiments got better, we didn't have access to collimated beams of neutrons or something, right? We just were able to manipulate continuous media, and that as we got closer and closer to the Compton wavelength of water, we saw that Navier-Stokes didn't work, and we kept adding in terms, right, to correct for the deviations from Navier-Stokes at these small scales. And if you never had access to those small scales, what if you didn't know? You could do your experiments up to some scale S. You want to extrapolate your theory beyond S, but you see that the theory's sick. It breaks down in some way that I'm not going to quite specify. Then you're presented with the option, right, as a theorist before the data comes in. So here's the theory. Our theories are going to be Hamiltonians. So this is our starting theory. And then we realize above some scale lambda. So just as a theorist, you sit, you do your calculations with your theory governed by some initial Hamiltonian h. And then one day you get infinity and you realize, oh, something's bad. And that is pretty great. I mean, that's a fantastic observation as a theorist because you've discovered that there must be something new. So the natural thing you want to do at this moment is to add in a correction that stops the theory breaking down above lambda, right? Should be a natural, I hope. So just without having done a single experiment, you can say, I need to replace my Hamiltonian with something that's basically like the original Hamiltonian, because we know that we've got to match what we've seen already. But then we've got to add in something to render our theory better behaved. I'm putting hats on because we may as well just admit that we're doing quantum mechanics now, right? So the constraints, there's some constraints. You can't just add in anything that you like. Whatever you add in, it had better match what we've already seen, otherwise you've made a mistake. So whatever you add in to fix it, let's call this the better match it, otherwise there's, you've made a mistake. So let's summarize. We're doing physics, we do experiments, we make observations, we find models for these observations, then we extrapolate. This is the key point, right? You extrapolate your models to apply to degrees of freedoms that you have not yet observed. And then you realize that there's a catastrophe. Because the theory that you extrapolate to apply to all these degrees of freedoms that you have not yet observed breaks down. And breakdown could mean many things, but just say it exhibits the presence of infinities in quantities that you know not to have infinities in. So the only thing left open to you as a theorist is that you have to correct your theory in such a way that it matches what we've seen up to some given observational scale S. And at the moment, I suppose that observational scale for us, if you ignore all the cosmological observations we've made, is something like 120 GeV. 200 GeV, I don't know. Now, this thing that you add in here, now you should have a legitimate concern, right? What can I add in here? Well, because there's an infinite number of degrees of freedom we have not yet observed, presumably infinite, there's like an infinite number of things that you could add in, infinite number of theories that you could add in to fix up your current theory. And that's true. That's really the case, right? We don't know how to describe the dynamics of degrees of freedoms near the Planck scale. It might be that there's an infinite possible number of theories that would do the job of fixing up our original sick theory. But the remarkable thing is that many of these ways you have of correcting your theory have no observational effect at lower scales. Now, this is the result of something called renormalization theory after Wilson, to Kenneth Wilson. So the first thing you might think of doing, you have all these possible ways of correcting your theory so that it does not break down. How many are there? Infinite, right? Infinite number of ways. So you try and parameterize all the possible terms you could add in your Hamiltonian to make your theory better again. And there's an infinite number. There's this list of terms which are polynomials in phi hat and grad phi hat and grad squared phi hat, pi hat, grad pi hat, blah, 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 forevermore, right? All these terms. So then what you do is you go, okay, let's find out what effect these terms have on predictions up to our observational scale S. It's a reasonable question. We have this infinite list of possible terms. It starts off with phi, with some. We can parameterize all these terms sort of with an infinite list of numbers. And then you could ask, okay, if this parameter d12 was non-zero, what effect would it have on observations up to scale S? And it turns out, and this is the remarkable result of Wilsonian theory, so this is the stunning result of Wilsonian renormalization theory. You have some Hamiltonian which works up to some cutoff lambda, and then you add in correction terms above lambda to fix it up so it doesn't break down anymore. And then you ask, of this infinite list of terms I could add in to pertain to degrees of freedom above this cutoff lambda, measured in inverse length, how many are actually relevant? How many actually lead to an observable effect at scales we've already observed? And the stunning result is only a finite number. at least for the scalar theories that we've been talking about, and in fact for other theories that we're going to talk about later in this course. Such terms are called relevant perturbations. And the list is given by these operators. There, in dimensions 4. Now to come to answering the question of what is a cutoff. A cutoff is any way you like to stop your theory pertaining to degrees of freedom above lambda. So however you like to implement it, you can do it that way. All cutoffs are related by an infinite number of terms like this, but only a finite number of them will have any effect on your predictions below the cutoff. So my favorite cutoff is for the moment, is the momentum cutoff. So I'll describe that before we finish. The momentum cutoff does break Lorentz invariance, which is sort of worrying, but it has other things that are good though. Okay, we have this expression for the Klein-Gordon Hamiltonian. And that integral is like over all momentum, right? So you just restrict that integral to go over just momentum with value less than p, lambda, sorry. 3 momenta. That's one way to fix your theory above lambda, right? It's like the simplest, stupidest way you could fix a broken theory. Is you just say, you're hereby not allowed to make predictions above the cutoff lambda. I'm going to remove all dynamics that are assigned to degrees of freedom above lambda. And then renormalization theory, according to Wilson, says that any other way you have of changing your theory to become well-behaved above lambda can only differ in these 7 terms up here from the way you chose here. So actually, all these cutoffs are related. So what we're going to do in the rest of this course is, I guess I'll emphasize this at the beginning of the next lecture, is every time I write down a Hamiltonian now, you have to understand that the Hamiltonian is written down with a cutoff in mind. I choose some value of lambda beyond which the theory is not allowed to work anymore. So even though I write down one Hamiltonian as though there is just this single Hamiltonian, really what we have in mind is a family of Hamiltonians parameterized by this cutoff lambda. And as soon as you add this cutoff, everything becomes finite. So if you add this cutoff in the way I've just described here, also on the interaction term, right? Phi-4 theory it has this d3x phi hat to the 4 in here. So when you cut it off, you replace this sick theory, it's legitimately sick, it's got infinities in it, with the same one as before. This is one possible approach. We're going to go into momentum space and cut off this integral here above lambda. And this is slightly ugly, unfortunately. So I'm not going to write it out now. So every Hamiltonian in this course is understood to only be defined in the presence of a cutoff. And the dependence on the cutoff is chosen so that the experiments that we've observed up to some given scale S are all modeled well by this cutoff Hamiltonian. We'll later on see how we have to adjust these coefficients here as you change the cutoff so that you still match the experiments that you've done up to now. But that's the real nitty-gritties of renormalization theory, and I don't want to get to that yet in this course. For now, just imagine that all our theories are correct up to some lambda, beyond which we have to turn them off. Okay, thank you very much.